Hey everybody, this is a new math puzzle. I haven't done one of these in a couple of weeks, so I thought I'd do another one. This one's kind of a fun little problem. So it's another math puzzle. This is called the light bulb problem. And here's the problem. There's 10,000 light bulbs in a room, and each light bulb is numbered 1 to 10,000, and each light bulb has its own switch, also numbered 1 to 10,000. And they all start off. Now outside the room, there are 10,000 people. And the way the problem works is the first person walks into the room and flips every switch, which turns all the light bulbs on. The second person walks into the room and flips every second switch, so number 2, number 4, number 6, and so on. And then the third person walks in the room and starts at light bulb number 3 and flips every third switch. Person number 4 flips every fourth switch, person number 5 flips every fifth switch, and so on and so forth, all the way through 10,000 people. Now the question is, when they're done, after all 10,000 people have cycled through the room, how many lights are on? And the second part of the question is, what about light bulb number 8,649? Is it on or off? All right, so that's our problem. I'll let you think about it for a couple of seconds and then we'll try to figure out a solution. Okay, so here's one way to solve the problem. And there's a lot of different ways to do it. You could do it on a computer, for example, or you could do it with Excel. But one way to solve the problem without any of that fancy stuff is to do a little mini version of the problem. So that's what I'm going to do. We're going to do a little mini version of the problem with 20 light bulbs and see what happens. And then we'll extrapolate that out to 10,000 light bulbs. All right, so we have our 20 light bulbs right there, and they're all off. And then person number 1 comes into the room. He starts at light bulb number 1 and flips on every bulb. So when he's done, all the bulbs are on. And then person number 2 enters the room, and they start at light bulb number 2 and they flip every second bulb. So that's going to turn off number 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Just like that. Then person number 3 is going to enter the room, and they're going to flip every third bulb. And from here it starts getting complicated. So you'll see number 3 is going to go off, number 6 is going to go on, number 9 is going to go off, 12 is going to go on, 15 off, 18 on. Just like that. All right, then person number 4 enters the room, and they're going to flip every fourth bulb. So 4 is going to go on, 8 is going to go on, 12 is going to go off, 16 is going to go off, and 20 is going to go on. Sorry, I think I said 16 was going to go off. It's going to go on, 20 is going to go on. There we go. Number 5 enters the room, and so on and so forth. And from here I'll just kind of flip through the slides until we get to about number 11 or 12. But it progresses the exact same way. So here's number 5. Boom. Number 6 enters the room. Then number 7. Then number 8. Then number 9. Then number 10. All right, now I'm going to kind of pause at number 11. Watch what happens with number 11. So number 11 enters the room, and he's going to flip the number 11th bulb, and that's really the only bulb he's going to flip, because the next 11th bulb would be number 21. I'm sorry, number 22, and there is no 22, so only bulb number 11 is the only one that's going to change, and it's going to go off. There we go. Now for 12 through 20, the same thing happens. Each time the person enters the room, for example, person number 12 would flip bulb number 12 and then 24, but the problem only goes up to 20. So number 12 is going to flip, number 13 is going to flip number 13, number 14 is going to flip number 14, person number 15 will flip 15, and so on and so forth. So from here on out, bulbs 12 through 20 are all going to get flipped exactly one time. So I'm just going to do that all at once and complete the problem. Just like that. Now, notice which light bulbs are on in our little mini version of the problem, our little 20 light bulb version of the problem. 1, 4, 9, and 16, all the perfect squares. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and those are the only light bulbs that are on. So, how many perfect squares are there between 1 and 10,000? That's how many light bulbs will be on. And the answer is 100. 100 times 100 equals 10,000. So 10,000 is the 100th perfect square. So there's going to be 100 light bulbs on. And what about light bulb number 8,649? Well, the answer to the question is it a perfect square or not? And if you take the square root, you find the square root of 8649 is 93. It is a perfect square. So light bulb number 8649 is on. And that's pretty much it. That's the end of the problem. We've solved the problem. Now, some of you may wonder, why does it work like that? So everything from here on out is extra. But why is it that only the perfect squares remain on? Well, the answer is because of the number's factors. In other words, the numbers which multiply together to make that number. And it's that way because factors always come in pairs. For example, consider all the numbers which multiply together to make 12. You've got 1 times 12, 2 times 6, or 3 times 4. That's it. The only other way to do it is to reverse those, but it's 1, 2, 3, 4, 6, and 12. Those are the only numbers that multiply together to make 12, and you'll notice they come in pairs. There's 6 of them total, and 6 is an even number. But for a perfect square, consider the numbers that multiply together to form a perfect square. We'll use 16 as our example. 1 times 16, 2 times 8, or 4 times 4. But that last pair isn't really a pair after all. It's one factor that gets repeated twice. So if we were to list out the factors for 16, it's 1, 2, 4, 8, and 16. It's an odd number of factors instead of an even number. And that's true of every perfect square. So the reason the problem works the way it does is because for any number that's not a perfect square, it's going to have an even number of factors. Each factor corresponds to one flipping of the light switch. So since the switches all started off before person number 1, all the non-perfect squares end in the off position. But the perfect squares all have an odd number of factors because of that one number that gets repeated, its square root. So for each of the perfect squares, those light switches get flipped an odd number of times. So since they start off, they finish on. And that is pretty much the end of the problem. All right, hope you liked this one. If you did, please click subscribe, hit the like button, comment if you'd like to. Nobody's commented on any of my videos yet, so let me know that you're out there and enjoying these things. Or tell me what I can do better. But until next time, thank you very much.